Matrices. So matrices are important for a number of areas, including cryptography, but also they are important in the area of networking. When you have routing tables in a computer network, you need matrices. And not only that, but in the area of information technology, matrices are super important when it comes to programming and developing software, representing data structures. So it's important that we understand the basics of matrices and how you can compute operations with matrices. So the first definition we have is of a matrix. The matrix is a rectangular array of numbers. So you have n rows and n columns. Usually, or not usually, but always, the first number represents the number of rows. The second number represents the number of columns. If these two numbers are the same, then we call that matrix a square. That's a square matrix. And we say that two matrices are equal when they are the same pairwise. So the element, ij element of matrix A is equal to the ij element of matrix B. The next definition here is row and column. So basically, the matrix is composed of rows or columns, whatever you want to see them. But the importance here is the ordering. So when we say that the first index belongs to the row and the second to the column, that's always going to be the case because we are following this definition. So we call these little components, each of them, we call them elements, or we call them entries. And remember, we're going to use the sub-indices I and j to denote the row and column, respectively. So let's take a look at some matrix arithmetic. When you have matrices, you can add them or subtract them. And to do an addition of two matrices, all you have to do is to do a pairwise addition. The only condition is that the two matrices must have the same dimensions. So when we say dimension, we mean the number of rows is the same in both matrices and the number of columns is the same in both matrices. The next definition is the product. So the product is a little bit tricky because it's not a pairwise operation. It's a pairwise operation and then some pairwise additions. When we do an exercise during the synchronous session, this will become much more clear. Perhaps one thing to note here is that a condition for two matrices to be able to be multiplied is that the number of columns on the left-hand side matrix must match the number of rows in the right-hand side matrix. So you can imagine that matrix multiplication is not commutable. Okay, so keep that in mind. So A times B is not necessarily equal to B times A. And of course, if the number of columns on the first matrix is not the same as the number of rows in the second matrix, then you cannot multiply those two matrices because they don't match the condition established in the definition. The transpose of a matrix. Before we do that, we need to take a look at the identity matrix. This matrix is a very peculiar one, and it takes it's important in a number of fields. One I can think of now is signal processing. But the definition of this identity matrix is it's a matrix which is a square, so it has the same rows as columns, and the diagonal, the main diagonal of this matrix is equal to 1, and all the other elements are equal to 0. Okay, so this identity matrix is kind of, if you're looking at scalar numbers, or the numbers we use commonly in multiplications, is like number 1. If you multiply 1 by any number, the result is that same number. Same in matrices. So A times the identity matrix is equal to A, or the identity matrix times A is equal to A. Now, the transpose of a matrix is the resulting matrix when you turn the rows into columns. As simple as that. We also say in another definition that a matrix is symmetric if its transpose is the same. The next topic is 0-1 matrices, and again the previous definitions were talking about real numbers that you can have in the matrices. In this case, for 0-1 matrices, the only possible values that the elements can get is either 0 or 1. So for this, we're going to use Boolean arithmetic, and we're going to think and in terms of what we studied during the logic section of the course at the very beginning, when we had the connectors, the and the or. So we'll need to use those to perform operations on 0-1 matrices. The first definition we have is the join. So the join can be seen as an OR of the two matrices. And to perform the join, all you have to do is have pairwise OR of the elements of the matrix. The condition is that they have to have the same dimension. So the number of rows and the number of columns in both matrices have to be the same. And the other definition is a meet. So the meet, as you can imagine, is the equivalent of the and. So if the join is the or, the meet is the and. And to compute the meet of two matrices, all you have to do is a pairwise and of a binary and operation over the elements of those two matrices. Another definition we have is the Boolean product, and this will finish our session here. But the Boolean product is, you can think of the product of two matrices of real numbers. And the operation is very similar to the product of two matrices, except that you substitute the multiplication by ands and you substitute the addition by ors. And the rest is the same. When we do an exercise during the synchronous session, this concept will become much more clear.